I know some of us have taken Calc 1. Others of us are going to, and you'll see what I'm about to talk about. Current. We've been saying that it's the amount of charge that moves by a point in an amount of time. Total charge going through delta Q over total amount of time, delta T. Well, yeah, but in this case, what if the charge doesn't move the same rate at all times? It's sort of like the difference between average velocity and instantaneous velocity, right? If we drop an object, the average velocity, sure, is the distance it fell divided by the time. But the instantaneous velocity, right at the beginning, is small, is less than the average. Right at the end, just before it hits the ground, has to be greater than the average. So we're sort of papering over the variation in current by only talking about the average current as the total amount of charge for the total amount of time. If you want to look at the actual current as a function of time, what that means is that you're letting the time interval between different times when you check, right? What time is it now? How much charge moves through in this very small amount of time? All right, use an even smaller amount of time. How much charge moves through in that amount of time? And the smaller we go, in the language of Calc 1, we're taking a limit as the denominator goes to 0. We can't actually divide by 0, but we can take a limit. We can let the denominator get as close to 0 as you want without actually being 0. And that means we're taking a derivative. We're asking at what rate is charge moving through at this time? How fast, how much charge per second is moving through now? Now, this gets us the current as a function of time. Now, the current moving through the circuit, we have a function for it. As a function of time, at any instant of time, we wrote that the current has some maximum value times an exponential. This is an instantaneous current. Tell me exactly what time it is, I can tell you the current. It's not an average. It's what is the current as a function of time. Now, the current, we said, was the voltage on the battery divided by the resistance. The function for Q didn't come from calculus. It came from voltage. It came from the loop rule, and then the definition of capacitance. So that's safe to use. We started with this function for current, and then we used it. So actually, we can still use this function for the instantaneous amount of charge stored on the capacitor. Q0, 1 minus e to the t over tau. Now, Q0, we said, was the charge, or no, the capacitance times the total voltage that we were eventually going to put, I'm just going to call it V0. the total voltage we're eventually going to put on the capacitor, the asymptotic percent difference across the capacitor when it's fully charged. The time rate of change. All right. Capacitance, battery voltage, those are constants. I can multiply now, or I can ask for the time rate of change of this expression and multiply after. So I'm going to multiply after. And this d over dt, that's a derivative. But what we're asking about, here's a function. 1 minus e to the negative t over, this is some function of t, right? I'd like to know how much it changes. What is the change in this function for a very small amount of time, delta t? Let's find out. The change in the function, so the function has a new value, delta t later. 1 minus e to the negative t plus delta t over tau. How much did the function change? It's the difference. It's one minus the other. We got to divide by the very small amount of time, delta t, that went by. All right, let's see what happens. I'll erase this for now. I'll put this back, don't worry. The limit, as delta t gets really, really small, of this. All right. Delta f is the new value minus the old value. So it's this noise, 1 minus e to the negative t plus delta t over tau, minus the old value, 1 minus e to the negative t over tau. And we divide all of that by delta t. All right. Distribute the one, or distribute the minus sign. We get minus 1 plus e to the stuff. Let's separate this into two fractions. Negative t over tau, distribute the minus delta t over tau. That's this exponent is this exponent, just written as the subtraction of fractions as opposed to this weird like common denominator form. All right. Now, when we multiply, we add the exponents. Right? So this looks like what happens when we multiply combine the exponents. So I'm going to make that switch. I'm going to write that as e to the stuff times e to the other stuff. 1 minus 1, e to the negative t over tau shows up twice. Let's factor it outside. What we're left with we got one from here minus one of them from here minus e to the negative delta t over tau. You still got to divide by delta t. And now we do the limiting thing. Delta function over delta t was this noise, but now we got to take what happens if delta t goes really small. If delta t is really small, let's pretend it's 0 just for a second. E to the negative 0 is 1, because anything to the 0 power is 1. 1 minus 1 is 0, but we're dividing by 0. And the logic here is that as delta t gets smaller and smaller and smaller and smaller, this thing in parentheses gets smaller and smaller and smaller, the same way that delta t does. That they go to 0 like equally fast, which means this starts to, as the smaller delta t gets, the closer to 0 this is, the closer to 0 this becomes. If delta t were 0, they'd both be 0. So let delta t be just infinitesimally bigger than 0. The denominator is just infinitesimally bigger than 0, but so is this thing in parentheses. That's like super, super, super small thing divided by the same super, super, super small thing. It's like 1. That's the piece. That's the thing we needed. Okay. We put back what we had. That was the rate of change, but we pulled out the capacitance and the not velocity, but the total potential difference we expect across the capacitor times the rate of change of 1 minus e to the negative t over tau. But this thing is what I just said was e to the negative t over tau. Hang on, I'm missing a piece. How did I miss a piece? Oh my gosh. You gotta stop me when I make mistakes like this. Just a second ago, we've pulled out e to the negative t over tau. And then we had 1 minus e to the negative delta t over tau. And we're going to divide by delta t. In order to really get the full story, I have to use an approximation. There are other terms here, but it's about right. It's good for very small values of x, pretty close to 0, which is exactly the kinds of values of x that I'm talking about. The exponent here is very, very small because delta t is very, very small. So this is actually a good approximation. So I'm going to use that to modify this. Subtract e to the something. That's like subtracting 1 plus that something. That something in this case was negative. So 1 plus the negative thing. Let's put that there. It's not super convincing, but you can try it. E to the 0 is in fact 1 plus 0. E to the 0.01. Try it. Is 1.01. Like it's eerily accurate. All right. If we do that, distribute the negative, -1 plus that, the -1 minus 1 cancels. We just left with delta t over tau. The delta t's canceled, but we've got a division by tau, which is going to get tied up with this thing. We don't even need to worry about the limit as delta t goes to 0. That is the thing that allowed us to use this approximation. We're good to go. It's the extra factor of tau that I needed. That division by tau, I gotta have it. Sure, those of us who've had Calc 1 will look at this and say, well, yeah, you get it from the chain rule. But that's not super useful to those of us who haven't yet. So I wanted to kind of bring, tell the story in a way that was convincing to folks who haven't yet had Calc 1. And this is the best I can do. At least the best I can do at 9 o'clock at night. So, the capacitance. The potential of fully charged. The derivative is this thing that I've been talking about. We do have an e to the negative t over tau, but this extra factor, this extra division by tau is really important. That's the thing that lets us cross multiply, cancel the voltages, cancel the e's to the negative t over tau, They're the same on both sides. And RC on this side is in fact equal to tau. Maybe not the most convincing proof you've ever seen. This bit with the approximation feels a little bit like, don't look too close. Although if you try a bunch of different values very, very close to zero, you'll see that it is a really good approximation. And then we can, once we sort of justify that we can use it, there we go. All right, that's it for now. Thanks, everyone.